So this is something that Kevin and I have pulled together explicitly for this session, but it's something that we've been using to begin with kind of subconsciously, and then after that more and more consciously on lots of projects that we've been delivering over quite a few years. But what we wanted to do is kind of pull it together into something which we could present to the audience here. So we're really looking forward to the questions at the end, but we'd also like to get feedback as well. So if anyone thinks you'd be kind, but if you think it's barmy or just won't work, or if you've missed something or it's not clear or whatever, then we'd like that feedback as well. And if you don't want to speak to us while we're standing at the front, come up to us afterwards, or we're at the Capgemini booth because we're hiring, or we're giving away t-shirts as well. So if you want to work with us, come to see us at the booth. But anyway, so who are we? So I'm Andrew Harmel-Law. I lead the Java team in the UK. But that's a sideline. In my day job, I look after the integration tier and the API layer for a major household name company. So the availability, the performance characteristics, the flexibility, and all of those kind of aspects of that tier are directly my responsibility. So I look after the team and build bits of it, but also my neck's on the line when things don't work as they're supposed to.
I'm Kevin Rudland, so I'm a technical lead on a very large government project at the moment. I can't really tell you anything about, but it's kind of really important, it's really cool, it's really difficult, it's unique, and it's one of those problems you can't Google it because no one else has solved it. So I'm on the hook for making it work and a technical solution.
So because we're taking a scientific approach, we've taken a scientific approach to the presentation. So we've split it into sections that you would expect to see if you're reading a science paper. So if any of you have done science degrees, you should recognize the kind of core elements of the presentation. So the first thing is the abstract. And as it says there, it's a bit you write at the end after you've written the rest of it. But what we're going to do here is we're going to tell you what we're going to tell you in the best tradition of all presentations. So we, hopefully over the next 45 minutes, are going to present to you a proposal that we have, and hopefully it will be borne out, that as we move towards more and more hyper-distributed systems, so at the moment they're called microservices, but basically taking what used to be one or two large chunks and splitting it up, that the way we conceive of those and the way we kind of test the non-functional aspects of that needs to change. And the way we think we can do that in a meaningful way is to use the scientific method. So hopefully this will prove useful. So next up's the introduction. We've split the introduction into two pieces. Traditionally, again, the introduction is kind of where you set the scene. So what we're going to do is introduce you to what we currently think is the problem. That's the first part of the introduction. And then the second part of the introduction, we're going to quickly introduce what we think is the solution. And then we'll go into it in more detail. So this is a slide I've stolen. I've also used this on my other presentation that I'm doing with Gayatri tomorrow. But I think it's super illustrative of where we see ourselves either right now or where we see ourselves going. So Netflix is a terrifying example, but you can see that this is the interconnectivity diagram of all of the microservices that make up the Netflix service. Guilt looks less terrifying, but then you realize that there's only 12 out of 450 of their microservices. So I'm sure if you put the rest of those microservices up there, it would be equally terrifying. And Twitter is so terrifying it looks kind of beautiful because of the way they've laid it out. So this is, all of these guys have done this for reasons. They haven't just accidentally stumbled across this. But what they've done is they've taken the kind of aspects of their system and split it up. So they've not just taken one piece and split it into multiple pieces. They've connected those pieces across networks, which, as everybody knows, are unreliable. They've plugged them into third-party web services, which everyone knows are unreliable. They've gone even further in most cases, and they've put them on rented kit, which everyone knows is unreliable. Not to say that it used to be reliable before, but at least we kind of had, when things were more stuck together, we at least had a kind of vague idea that things were predictable.
It's my
turn. Oh, sorry, no, it's not still me. So I wanted to do a quick bit of audience participation. Who here does everyone agree with that? Are we kind of in the process of losing control over the systems that we build? Are we kind of reducing the level of predictability by consciously doing this new architectural approach? Are we consciously losing the predictability? I think we are. Daniel agrees, that's fine. No one in my team agrees. That's worrying.
Right, so picture of Elon Musk. So his name's come up in a couple of talks today. But the key point here is he was interviewed recently about what makes him successful in what he's doing. And one of his key points was he kind of applies first principle thinking. So he's applying the principles of physics to what he does to enable him to do things slightly differently and kind of break the traditional way of building rockets in this particular case where he's interviewed. So this is our kind of counter proposal. So the proliferation, actually, the losing control is actually it's a good thing, as this person clearly thinks. So the scalability is up, resilience is up, service availability, maintainability, kind of all your traditional like NFRs can be a lot better. Time change can be down. I kind of proposed the control we had before was a bit of a myth. You know, things still failed. It's just we kind of thought we owned it. Now it's someone else's computer and it still fails. You still have the same problem. It was kind of never in control in the first place, really, in the traditional sense. So, kind of rather than losing control, I propose we never really had it in the first place, really. You know, boxes still fail, disasters still happen, business still change their mind. It's all the same stuff. It's just now a lot of it's running on someone else's computer, which is now called the cloud.
And so that's actually something that I agree with. So, but what I think the fundamental change, and this is the point we want to make in the introduction, we have consciously decided to change the way we build systems, change the way we deliver systems, to change the way we interconnect systems, scale them and everything. We've consciously decided to change all those things. But we still need to guarantee or assure to ourselves that we have all of these gains. You know, we can't just take it on trust that we've gained all of these benefits that we just saw in Kevin's slide. And so that's what we want to talk about.
So there's a quote here. It's come from the Phoenix Project. Great book. The kind of key thing here is that the hypothesis-driven culture requires everyone to be a scientist, taking no assumptions for granted and doing nothing without measuring it. And why is that important? Well, it's time is valuable. We don't have time to do everything. Spend years deploying code that doesn't work isn't really of much use for anybody. So what we want to do is build on this. So things like hypothesis and scientist, really, they should be things that should be in our vocabulary more. They should be a bit more thought out. If we're not doing those kinds of things, I'd argue you're probably just guessing and hoofing it, doing it on ad hoc.
And so it's kind of at this point when we were looking at these things and seeing the use of the hypothesis and a scientific approach popping up in other areas of what we do in software development, we realized that perhaps we should start applying this to the non-functional testing that we do. So we kind of had a three-stage enlightenment. So number one was we've got to let go. We should stop trying to pretend that we have control and predictabilities in these things. And by doing that, we'll free ourselves up to do a lot of other things. And as it says there, we probably didn't have control in the first place. But what we can still do is test. But if we're testing, how do we focus our testing? How do we know that we're testing the right things? How do we know that we're not wasting our time? Because our time is valuable, and we want to spend all of that time in the right place in the right way. So this is the same hypothesis we showed you in the abstract at the start. We think the way to do that, and we've been trying this out for years and years, that taking a scientific approach, formally or informally, and like I say, we've only recently started doing it in a semi-formal way, it has massive benefits, and hopefully you'll agree with this.
So let's slightly scope up behind us. We're now ready to start diving into some of the details for what it might mean for us. So the first thing is quiet knowledge. The scientific method is a body of techniques for investigating phenomena requiring new knowledge.
And given the fact that we've lost predictability, we need to kind of gain knowledge about the thing that we've built to understand how it is working as we've built it, as opposed to how we hope we've built it and we hope we've met some NFRs. So if we keep following the train of thought, in science you famously have theories. So science is driven by theories. So if we follow this through, what are our theories in the world where we do things? And so probably our non-functional requirements are our theories. Until we've tested them, just like a theory, we don't know if they actually apply. So they kind of live in the same space as theories. But they're detailed statements about what we believe to be true, which is key, so just like a non-functional requirement. So here's a quick example. So we apologize in advance, we've got some slides with a lot of words on them, which we know is breaking presentation rules. We're going to share this deck afterwards, so we're going to quickly highlight some of the things, and we've also even diff-colored some of them, so you know when we've changed things from a previous slide. But here's some examples. So there are things that you should be more aware of, things that you probably see in your day-to-day life. The thing that we want to point out, though, is sometimes you'll see things which are called non-functional requirements, but if you can't state them in this kind of format, if you can't state them in a way that sounds like a theory, it's probably not a non-functional requirement. So things like the system will be performant, there's like red flags all over that, right? Because that's not, how do I test that the system is performant? So you need to go back and you need to build that testability into those requirements.
So one of the key things is falsifiability. So you need to be able to disprove it. So basically what we're talking about here is you need your hypothesis and you need your kind of counter-hypothesis. Your kind of hypothesis is the thing you want to test for, but your kind of counter-hypothesis is the end result of that. It doesn't happen. So a good example would be I might have a hypothesis that if I feed my children lots of sugar, they'll become hyperactive. My kind of null hypothesis that I can falsify is that actually has no effect at all. That would be a good example.
You can try that with our booth later on, actually, and feed yourself lots of sugar and see.
Yeah. But the key thing is you've always got the kind of two opposite sides of it. So here we've got when X requests per second are sent to the service, it'll do as we expect. And the counter argument, so the falsifiable bit, the H0 is it won't make any difference at all.
So the next piece is it's a key thing in science, all of science, like the philosophy of science, and it comes from Karl Popper. So it's very easy to give yourself a false sense of security. So you come up with your theory, which is your non-functional requirements, and you design a bunch of tests which basically are quite easily validate that hypothesis, validate that non-functional requirement. But that's not really telling you what you want to know. What you want to do is design tests which may invalidate. So you need to put yourself in danger of, you need to test things at the edge. You need to test things at the limit to figure out if you really are meeting that requirement. And that's what it means here is a single counterexample is logically decisive. So Newtonian physics was all well and good until Einstein came along and then disproved the fact that, Newtonian physics can't exist in all places. But up to that point, Newtonian physics had stood up to a lot of testing and kind of experimentation. But what you need to do here is again, focus your efforts, and this is the first place where you can start to focus your efforts on a single test or a small set of tests which can help prove things. And this is where it's worth pointing out, we use this to kind of inspect and adapt and orient. We're not waiting till the end of a project to start doing this. As soon as we've got something built that we can test, we'll start testing it. And we'll go into how we do that later on. But as soon as you have a thing that you can test, trying to make sure that it really is giving you the systemic qualities that you're looking for is key. And then if you find it isn't, it's software development, so you can go and fix it, and you can change your architecture, you can change your implementation or whatever. So a few quick slides about things that are good areas to focus on. So number one is scalability. Loads of people always seem to assume that things will just linearly scale forever. This never, ever happens. If it does scale linearly, you just haven't scaled it enough, because at some point you will find some line of code or some aspect of your infrastructure which bottlenecks. So obviously, however, you don't test it to scale to infinity, but you need to test it to scale to a nice level above, which gives you a really good level of confidence that you can meet your scalability criteria. The next one is in SLAs and resilience. So again, it's nice to test. If you think you want to be resilient, but you've got a 99.999 uptime, if you do the math, that's ludicrous. So you need to know that if you're, if your mean time to failure, or if a node goes down, how quickly your Eureka server will rediscover your microservices. You need to test that and not just assume that it'll find them quickly. Your network might not be fast enough, or something might not respond, or things might time out. So it's good to see. And the third area is shiny and new. So we're all engineers. So I guarantee every single project we do, there's always a new thing. Or more than one new thing. So you can read the marketing slide, or you can read like the readme.md on the front of the GitHub page, and it tells you all the awesome things it does. Don't trust it until you've actually taken your code and implemented stuff on top of it, and then you've checked to see if it really does do multi-master replication with all of the data that you want, with the recovery times that you need, et cetera, et cetera. And so here's two examples of scary hypotheses. This is ones of a tolerance of downstream failure. So the H0 is it all fails over and it's nice and it all comes back and everything recovers, and if it's really bad, our circuit breakers kick in. The H0, the kind of the same test, but the alternative outcome that's possible is that you need manual intervention, things go badly wrong. So as Kevin pointed out before, it's not just important to think about what it looks like when it's good. What you also want to think about is what does bad look like in the same test. And just even the mental exercise of thinking of that is very, very useful.
This is quite a kind of famous thing. So Occam's razor, the simplest explanation is usually the correct one. You can apply this to loads of stuff in IT. Loads of those. There's everyday cases. Write the simplest possible solution, like the KISS principle, stuff like that. You can apply it to your NFR testing as well. So there's an American program, Mythbusters on Discovery. They have their small-scale experiment. Before they go and put a rocket on a car and fly it into a mountain, they'll put a firework on a remote-control car because it's a lot cheaper. You're basically building a model of the world around you. You want to do the simplest possible experiment to prove yourself wrong before you go to all this expense and effort of setting something up that's probably doomed from the start. You can also kind of scale back down again. If you have a big thing and it doesn't really work, well, you could try doing a small-scale experiment. You could try the simplest possible experiment to prove that actually you weren't right in the first place. So up until now, we've been talking about things being explicitly simple, but then we kind of dig into how we apply that scientific approach to things a bit more complicated, and look at some kind of tests and how we might prove, or sometimes more importantly, disprove ourselves. So the first one is be repeatable. So if an experiment can't be repeated to produce the same result, it basically implies your original results might have been an error. So this is basically tied to falsifiability. If you can't falsify it and repeat it, then it's kind of worthless. Fortunately, in IT, we have lots of automation. Most of our stuff is software. But sometimes it's really, really hard to do this. So, for example, if you're using a public cloud provider, you might have like the noisy neighbour type scenario, or maybe you ran your first test and there was a noisy neighbour and they've now gone away and the results get better. But there's kind of ways you can get around that. You can kind of run your tests repeatedly, kind of best of 3. You can kind of try and average things. So we'll get to why an average isn't a great idea. Even if you're on premise, you might have SANs, you might have backups, you might have other projects. It's very hard to find a position where actually you're not sharing anything at some point these days. The key thing is you've got to be repeatable. And if you can't repeat it, you kind of need to get to the point where you can repeat it before you even start.
So with that in mind, the next thing that we're going to just brazenly steal from the scientific method is a framework for thinking about the design of your tests. So in science, specifically the area that I study as well, in psychology and biology, experiments typically consist of 3 things, or 3 things that you kind of start off with, and the 4th thing which you measure. So those things are the subjects, the things that you're testing, the environment in which they exist, the independent variables, which are the bits you manipulate, and then the things you measure are the dependent variables, but we'll cover them in a second. So the subjects, it's possibly quite easy to conceive of, but there are hidden subtleties. Just like with when people do psychological experiments, we'll just get 20 people off the street. Doesn't work. So you might, which street are you walking out onto? If you walk out onto Oxford Street, you'll get 20 people who like shopping on a Saturday. You might not want that kind of thing. You want to have a good range. So the same thing for subjects. So what you need to do is get into the habit of thinking, how many of them are there? So that might be how many microservices are there? Is there 1, or is there 2, or is there n+1, etc., etc. How are they connected? Are they connected by running locally via localhost on your laptop, or are they deployed to the one, virtual machine that somebody kicked up for you in a quick test environment, or is it like a proper copy of prod? Does it have all of the prod networking? Does it have all the prod firewalls? All of these kind of things. All the things that will later come along and make you realize that what you thought was live-like wasn't. And what do they already know? This is one that we discovered maybe not at the very beginning, but it's key. So think, what do they already know is what is their base configuration? When you start them up, what state are they in? And also caches. So another way to make yourself convinced that you've automatically made something faster when you didn't is you set up a test, you run it and it's slow. Then you run the same test again, you run it as fast. You've warmed your caches. So you need to clean your caches out. Or if you start with a warm cache, you need to warm your cache every time. So all these things need to be consistent and repeatable. So with that in mind, we're going back to that first hypothesis, and we said we warned you there'd be a lot of words. The H1 and the H0 is still the same that we showed you before, but now we're kind of talking about the prerequisites, the things that are there in place at the start. So given n instances of ABC service with default configuration, request caches, blah, blah, blah. You'll see is also something that we don't talk about, but we use a lot. To simplify this, even though it's quite wordy, things like ABC service, default configuration are just kind of references to a wiki page, for example, which has the default, the definition of what we mean by default configuration, for example. So then when we need to repeat an experiment, we can repeat everything.
So the other thing is, so it's a bit cryptic. Absence of evidence is not evidence of absence, but we see this all the time. You get your nice shiny thing, you deploy it to your nice shiny test environment, you get loads of confidence, pat each other on the back, put it live, and it falls over. And worst case scenario, you're on the front page of the Daily Mail for some reason. Generally to be avoided at all costs. But the reason that kind of doesn't work is kind of all sorts of reasons, but you need to make sure you're live like is the key thing. You need to kind of know what went wrong. You need to kind of be aware of some of the shortcomings of your environment as well. It's kind of the false negative. So if you run a test and it worked fine, went to production, you find there are problems, you need to kind of know that extra knowledge of what is the difference between your production environment and your test environment, so you can then just kind of feed that back into the model. Some cases, you're not going to be able to fix it because of cost and money and risk and all sorts of reasons, but you need to kind of be aware of the things you don't know up front.
But I, as many people who work in my team know, I'm a student of Netflix. So Netflix famously just tests in production, although I'm sure they test in other places too. But it seems to me that, given the number of times where you think you've tested stuff and then you put it into production and you find the one thing that production differs from, or the fact that users don't use something, it seems relevant at least to posit the theory, the hypothesis, that the only place to really get valid results is by testing in production.
But that's not always possible. So, again, from science, the point here is to be ecologically valid, essentially saying you need to approximation of a real-life scenario. So you have a model, and you need to get that model as close as you possibly can to production. And there's loads of ways you can do that. Loads of things you can kind of control. Some of it's a function of cost, time, resource. You might have some legal kind of restrictions there, but it's things like the environment, so the configuration of the environment, the data, what is it actually running on? You might have a test environment on one hosting provider, production might be on-premise, or vice versa. If you've got monitoring in production, you need to have monitoring in dev or your performance test environment. It needs to be the same everywhere you can. You also need to look at what kind of scenario you're running in. Are you running in a normal scenario, or is it a DR scenario you're trying to test? Is the thing failed over and it's kind of struggling on? What other kind of external influences are there, and what kind of events can happen to your system while you're testing it? And the list goes on. This is like a really, really short list. The other kind of thing is some things like connectivity can be really, really hard. So typically on quite a lot of projects I've worked on, some of the external systems are these horrible old mainframe systems that have been running for 20 years that are doing a really important job, and there is only one of them. You can't change it. You have to treat it really, really carefully. So then you have to look at other things. You might need some kind of simulator or a stub. But then again, there's limitations. You need to be aware of what the limitation is when you do it. You might have another scenario where just because your organisation might be able to spin up an environment in 5 minutes flat, whenever you feel like it, doesn't mean the third party you're talking to can. So very often if you're working with a client, they might only have a deal with a third party for a production environment. Pre-production might cost a lot of money they just don't have in their budget. Again, you need to work out where your connectivity is and what your environment looks like, what the limitations are, and you need to kind of work out how you're going to minimise that risk on all of it. Some things might not be a risk. You might be happy with that, and then you test it and you find a problem, and then you change your opinion. So another kind of couple of things you can do. So in some environments, you might be able to take up a copy of production data. If it's personal data, probably not. You could take a copy of production requests, so you could replay production requests across your system, so it behaves in a live-like way. You could kind of do like a study of your production environment, and then basically use that to inform yourself about what is the difference between your test environment and treat your test environment like a lab. There's kind of other things like you can look at things like backup, schedule maintenance, all that kind of stuff, and even human factors. So the classic example in the UK is tax returns. So everyone needs the tax return to the last minute, and then suddenly they all submit it. That's kind of semi-predictable, but no one really knows how many people leave it to the last minute because it's human beings. If you work in, say, financial services and suddenly there's a run on a bank, loads of people log on, they'll all check their balance. So there's lots of things that can happen that weren't even kind of foreseen. Human beings and the news and media can even have an effect on your system. but one of the kind of biggest things we can kind of play with to some extent that has a massive effect on your tests is data. It's probably the easiest to change to some extent, but the main thing you need to look at is kind of a naive test would be, I'm going to throw 100 customer requests per second at this particular service, but not every customer request would be the same in real life. So some kind of good examples would be things like if you had a customer in orders, well, not every customer has the same number of orders. Some will have lots, some will have none, what's the average number, what's the distribution of those. If you have mandatory fields, how many customers only fill in the minimum mandatory field? Some, how many kind of go to War and Peace and fill the whole thing in? And that kind of different changes in data, you could almost think of it as giving the data a shape. But that shape is really important, because if you naively just test it with every customer has one order, for example, and then you go live and you find actually they're really loyal customers and they'll have hundreds of orders, you've got it 100 times wrong, potentially. So you can kind of learn quite a lot about that from the system you've built. So you can look at your data model, you can look at one-to-N type relationships. Where you've got one of those, you need to ask yourself, well, in real life, is it always 1, or is it 2, is it 10, or is it 1,000,000? That has a big impact. If you've got fields that are nullable, well, when would they get filled in, if ever? And after that, you can start to come up with an understanding of the way your real data looks like. You might be able to look at production and compare it. You might do things like invest some time in building a data anonymization, so you could kind of point at your production database, kind of swap names around, postcodes, that kind of stuff. So it's not real data anymore, but it still has the same shape, still has the same integrity. You could do things with, say, locations. Okay, you don't want to use real customers' houses, but you could use safe locations like your office, for example. There's lots of things you can do to make sure the data still has that same shape as the real data, but it's not real data.
So with those two prerequisites in mind, the next step is the manipulation of the independent variables. So that's the kind of interactions that you're faking with the system. So for this, we use JMeter. So there's a load of other ways to do it. There's lots of other tools. We use JMeter because it does what it says in the tin. Everybody knows how to use it. You can script the hell out of it. There's a million plugins for it these days as well. So a good tip is if you open a JMeter project that someone sent you and it doesn't open, it's probably because they've used the plugins that you haven't installed, so you install the plugins. But it just does what it says in the tin. It integrates with Jenkins, so we can put it into our continuous builds, and we can fail builds if they go too slow, and it gives you a nice automatically generated report and all these kind of things. So the screenshots, which are completely illegible, but the details all been fuzzed out anyway, is just kind of the screens that you would see if you're using JMeter. So if we're going to start, really naughty bit of performance testing, what we're probably going to do is start off with a bunch of hard-coded success requests. So here we're sending in some stuff to a SOAP API, because some people like Kevin and I, unfortunately, have to still work with SOAP. We just nabbed one that worked from a dev, probably, pasted it in, amped up the number of threads and requests per second, and just ran it and saw what happened. So that's cool. But we're proper hardcore engineers. So we realized that we also, maybe, sometimes people send in bad requests. So then we've got a separate thing. We're going to try to send in some bad requests, right? So when we run our test, we're not just exercising the kind of happy path. We're exercising the validation and the building up of the horrific SOAP fault message and all this kind of stuff. And so again, what does this look like when we put it in into the thing? You can see we've now got H1 when a mix of XXX valid requests and YYY invalid requests, and that's all we've changed. I don't know what's happened to the green. It should be coloured in green. So in this story, this did actually happen, but we actually did a bit more than this. You could deploy it and then watch it for an hour, deploy it at 4 a.m. and watch it for an hour and feel really smug and then go home because it's sawtooth things. So this is heap memory. And you come back in the morning and then you can see people have started using it and it's awesome because it's not memory leaking. That's called a memory leak. And then because you're only watching an hour, it looks really good. So then you stop watching it and you leave your Nagios reports to kick in. Around about here, the Nagios report starts kicking in because we've hit a high water mark. So then we panic and run around and wonder why things look like they're leaking when they didn't leak in our test because we soaked it for 6 hours, 8 hours, right? Nothing leaked. It turns out that we had made a request dynamic. So this is the bit we do here. You can pick things and make them dynamic. What we hadn't realized was that, as Kevin pointed out earlier, in real life, they were more dynamic. But also, not only that, we were using hystrix, and we transposed a string argument to our hystrix circuit breaker. So hystrix takes two things. It takes the key for the command object, which is like the circuit breaker in question, and then you can turn on request caching in hystrix, and it'll go, all right, this is the key, the request, so I'll look for that request in the circuit breaker, and if it's already there, I'll get the same response back, so I don't even need to go to the downstream system. If you get that the wrong way around, you've suddenly created a hell of a lot more hystrix objects, which if you're creating them fast enough, will start memory leaking. So what we did was, we made our request more dynamic, replicated this leak, and you can see we're doing it, this is all within real time, right? So that was a real graph. So this is as we approach midnight, and then we deployed it at midnight, gadunk. So we found a problem, we made it more dynamic, properly dynamic. Ideally, we wouldn't have found it in production, but this was a very strange kind of use case which nobody had foreseen. And we fixed it straight away. So no downtime, because we had microservices and all this kind of stuff. But it's important to point out, so you can make things very dynamic. So the one we saw before was just selecting a value between 1 and 100, but JMeter can let you do things like select, you need to select a country. Here, this one just picks one of the country values from random, but as Kevin pointed out, maybe you're in the situation where 50% of requests are for the UK, so you pick GB 50% of the time and do all this other stuff. So being realistic at this level of granularity sometimes is irrelevant, and other times is ludicrously important. And then this is just a picture to show you how we use it, which isn't very exciting. But you shouldn't stop there. So when you've got that, you'll have probably built up a bunch of point tests which test the creation of a thing, the deletion of a thing, the change of a thing from status A to status B. By building up all of those separate things, you're building up what, if you think about it, if you take a step back, is actually a really good suite of tests which give you the ability to make a really nice live load type mix. So when you've got all these tests, you can start running them, all of them apart from the one you're testing, as a base layer of kind of request volume. And then on top of that, you run one request with your good and bad request and your dynamism, all that kind of stuff on top. So then you're really getting a pretty good idea of a pretty sane, realistic usage of your system with all of the different interactions. People doing this, setting up accounts, deleting accounts, changing their details, ordering a thing, taking away a thing, etc., etc. And so that's this here. So somewhere we've got the word background load.
So sometimes stuff just happens outside your control. So this is Krakatoa, which was exploded and caused climate carnage all over the world for a number of years. But there are ways to simulate this kind of stuff. So there's things like the evil test harness. There's the simian army, for example, will go around causing fairly major disasters to your infrastructure. Most projects will talk about DR scenarios and it's failed over, SLAs and that kind of stuff. But the key thing from this is you really do need to test it. It really will happen. Nothing will cause a disaster quite like a press article very often when everyone logs in 10 o'clock at night because they've seen something on 10 o'clock news. And it happens all the time to most systems at some point, especially when you're feeling quite cocky and quite happy yourself. Something like this normally happens, or a data center outage or something like that. So the key thing here is you can change the independent variables. So your requests per second, your number of users, concurrent users, your request mix. So Andrew talked about the kind of background load. They're all the kind of dials you can change all the time. But the important thing is as you're changing those, you're measuring what comes out the other end, and you're re-baseline all the time. So again, if you've watched Mythbusters, they kind of do their small-scale test for blah, 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 and they start it. It's a really good habit to get into, recording your test results in a very kind of easy, simple way. So this is the scenario, this is what I did, this is what came out. This is the scenario, this is what I did, this is what comes out. So you've got it all. And at the end, when you want to go back and do some analysis, say, well, maybe that change didn't work, or maybe that one was better. You've got it all. And the key thing as well, you're changing one thing at a time. So it's very tempting to think, I know what I'm doing, I've read a tuning guide for blah, 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 and changed 10 things, that you don't get what you expect. If you change one at a time, you genuinely understand what you're doing. Again, it's not guessing, it's a controlled, scientific, methodical approach to doing something.
So if we return back to our second meta hypothesis, the kind of smaller, you only need to test in prod, we'd argue we agree, there's no substitute for simian armying yourself to death or game daying everything, all the time. This scenario won't catch every single Krakatoa-like thing, But if you kind of relied on something like that, or just relied on stuff happening in prod without testing a good deal of the things that which you know are most likely to happen, and you can learn so much and fix so many things in your system, it's definitely worthwhile testing outside of production. There's lots of ways that you can very quickly, very rapidly build up a nice level of confidence in the core infrastructure of what you've built, the core SLAs. So with that in mind, we're now into the results. So we've run our tests and we've collected some stuff.
So again, to be termed scientific, you need to be empirical or measuring it. So it's not about coming up with, if you're just coming up with something and you're not measuring it and you're not writing it down, you're probably just guessing. I suppose it's a bit harsh, but I genuinely believe that's true. If it's worth doing and testing, it's worth writing down and recording for somebody else. The most accurate way to do that is using maths and a bit of statistics. So you do something, you write it down, capture it on a wiki, however you want to, but you need to measure something, some quantifiable way, so you can go back to it later on. And the thing you're measuring is in scientific kind of lingo, it's the dependent variables. So a good example would be if you've got an electric bar heater, you put electricity in, that's your independent variable. Your dependent variable is the temperature of the thing, or how much heat it's giving out. In IT, you've got some kind of classic ones. So latency and throughput are dependent variables. So you can kind of design your system to try and give you the highest throughput and the lowest latency, but you can't buy a system that says it's 5 or 10 or whatever unit you want to measure it as. It's dependent on other things. So this is a classic kind of throughput graph. So a while ago I worked on a project where we were performance testing. We noticed our throughput rose steadily as the number of requests went in. So our dependent variable was kind of matching our independent variable up to a point. And then we had like a bit of a hockey stick and it all fell apart. In the end we kind of discovered that we were using a queuing system. On my Mac it kind of flew. In our wonderful cloud environment it didn't. And what we kind of found quite quickly was that the disk is actually attached via a network device. It's not actually a physical bit of storage, not something that gets shown, which is why a hybrid drive on a Mac is faster than a load of OpenStack VMs. And that was quite an important thing. So we had this theory that we'd kind of turn one dial and we'd watch the other thing, the measuring, go up, and it just didn't work out that way. So we had to go back. We basically found our H0. We had to go back and reprove it. Again, response time. So I think most people, if ever use a database, will probably have seen the scenario when this doesn't work. So it's all going nicely. You're ramping up the number of users, and then it just goes boom off the top of the graph. System falls over, and then you realise you didn't index one of the tables, and it's doing its best to keep up to a point, and it just catastrophically fails.
So with that in mind, we're at the discussion, which I think is the penultimate section. So again, another tip from science. So you've done your experiment, you've run your tests, and you've got your data, you've got your numbers out the back. One thing that's ludicrously important to do, and which we've seen people forget about all the time because they look at the data and the data looks good, is to tally your counts. So it's as simple as, if you know you sent in 50,000 requests to create something, you should be able to look in your persistent store and find 50,000 things you created. Because you'd be amazed at how many times you don't. And you should also check your logs for error. So it's simple, you can grep, right? So if you've got like error or warning, you can grep for them, and you should attribute all of them. Because sometimes you might, if things are nearing a bottleneck, you'll start seeing failures and retries, which is good, which is fine, it's your system working, but it's nice to know that that's the kind of point you're getting to, so you need to be aware of it. And the third thing is resource utilization. We've done this sometimes, and it's amazing the bits of your system that can spike CPU without you really being aware of it, because if you don't look at it, you don't know. It's still working. It's still giving you all the throughput you require. Well, the I/O is going crazy. And as long as, if you're at 90% I/O, it probably still looks like it's working fine. But if you push it a little bit higher, like Kevin said, suddenly you've got a bottleneck. And if it's distributed, stuff like starts falling over left, right, and center. So it's really key to know where you're going and kind of what resources you need, and then you can tune things. So next bit, though, with that in mind, if everything is still happy, you can start looking at your output, your numbers. And this is where stats comes in. So apologies in advance if you know this. So some people do know this, but other people don't. And I was subjected to 4 years of stats at university, so I'm now going to spend 6 minutes subjecting you to stats. As Kevin pointed out earlier, the mean means nothing. But the amount of time where people say the average response time should be X. And we're like, oh, that's awesome, because average is really easy to do. What we should be doing, and what we go back to our clients and say is, the mean is not the representative thing. There's a better way of doing it. And this is where we talk about the impacts of statistical distribution. That is where you get your predictability. So this is your standard output you get from JMeter. The one at the top is the one you look at. And then if you can't really see it, but there's a really nice low at 4 milliseconds and below the average. So that looks awesome. We're typically average, less than 4 milliseconds. This is fast. Then you probably ignore the red spiky bit because that's a bit scary. You need to probably ignore that entire graph. What you need to do is look at the histogram. And what the histogram is trying to show you is this. It's a normal distribution. So the normal distribution appears, it's also known as the Gaussian distribution or the bell-shaped curve. It's like a fundamental universal property of things that if you measure something more than once, you will not get the same result. But if you measure enough of them, you will get something that looks like a bell-shaped curve. So it might be response time. So long time at the right, not very long time at the left, and then the number of that response time. So if you look at that, then you look at the mean, which is the bit right down the middle, or if you're slightly skewed, your median is less and your mean will be off to the right. You're missing loads of stuff. You don't know how many are longer and how many are slower. So if you go back to JMeter, this is a better example of that kind of bottom graph. You can see we've got kind of pretty much a bell-shaped curve. But again, you can see average. So our average is to the left of 500 milliseconds. So we're double thumbs up. But our 95th percentile is slightly north of 750 milliseconds. And this is where percentiles, or in statistics, standard deviations come in. So this is another thing to point out. So standard deviations in the world of psychology, all they care about is the distance either side of the mean. So one standard deviation, which is the -1 and the 1 to either side of the mean, gives you 68.2% of your results. So 68.2% of all of your recordings in this example are within that kind of dark blue square. If you go 2 standard deviations, which is almost approximate to 95th percentile, 95% of your results, that's within the 4 bits in the middle. And that's what you really want to start caring about. But there's something interesting to point out, that if you're doing this with JMeter doesn't count from the middle out. It counts from the kind of 0 all the way up. So now you see 95th percentile. That means that everything from 0 all the way up to just over 750, that's 95% of your results. And that's what you care about. Or you might want to go 99th if jitter is a really important thing. So then 99th percentile, you can see, is probably well past 1,000, kind of 1 second. But you can still see there's some, like 1.250 milliseconds. If you've built up a microservices system where a service calls a service calls a service, if one thing's jittering a little bit, that gets magnified all the way up to the top. So you need to know some of your low-level services, the ones you know are fast, if they jitter a bit, that'll bubble up. So we put this into our increasingly verbose slide, which now says 95% will respond correctly within a certain time. And finally, when you've done this, then you can decide if you've passed. So we've taken you all the way here, and now you get to do a red light or a green light.
So, conclusions. So, run a test, we've collected our data, we've recorded it, we've looked at it in light of our requirements, but we might not have seen what we were looking for. We didn't validate our H1. So, the sort of things we'd hoped we'd kind of recorded as we went along. There are observation events. So, for example, did we have logging left turned up high? I think most people have done that at some point. I think it doesn't work. No, it's set at finest or trace. Was the test run properly? Did we warm caches up? Was the database in the same scenario? Was it even run at the same time of day? If we run some environments that got lots of backups and lots of peaks and troughs, and it's on shared infrastructure, time of day can affect it. Time of year can even affect it in some places. Were we measuring the right things? So what we need to do is basically look around, have a bit of a think about it, revisit your hypothesis and you kind of counter your null hypothesis, and maybe apply the Occam's razor, the simplest possible experiment to prove yourself wrong. So it didn't work out the way I thought it was, come up with a hypothesis for why it didn't, and then just go and test that one thing. And if you can do a small scale test really quickly to prove yourself right or wrong, that's obviously better than rerunning the whole thing. But the key thing is only change one thing at a time. Do the simplest possible test to disprove it, and do one thing at a time, and just keep iterating on it.
There is an upside, though. This is the first slide, which is where we're not stealing from science. Unless you're doing things like genetic engineering and on the kind of slightly questionable boundaries of science, we built the thing, and we can tune the thing. So if it doesn't do what we want, we can also just make it better. So we can fix a bug, or a memory leak, or tune the thread pool, or look at, tune the JVM, or all these different things. So we can also, there's lots of things we can go back to do. But there are 3 things you need to bear in mind. So number 1, will it have the desired effect? So correlation does not equal causation. So that's like, again, it was hammered into me at university. So just because if I do this, that happens, doesn't mean that this makes that happen. It just means that, something else or something over here kind of affects both of them. Number 2, will it have side effects? Because you can tune, so the thing we see all the time is people go, we need to give the JVM more memory, which is awesome until it tries to do a whole garbage collection, and then you wish you had less memory. So don't give it more of something. If it doesn't need more of something, give it the right amount of something. And then the last thing is, which is always confusing when it hits you the first time. The standard advice is find the slowest thing and tune the slowest thing so things will go faster. Until you tune the slowest thing and it then completely DDoSes a downstream thing, which is even more resource constrained, and the overall result, especially in a microservices environment, will that everything will go slower. And you're like, I've tuned it and it made it go faster, but then everything else went worse. That, everybody hits that at some point. And then when you're like, oh, okay, you realise.
So after you've done your tuning, again, re-baseline it. You make one change, rerun it, baseline it, keep examining your hypothesis, and just keep going round and round and round. It's not about a big heavyweight process. The whole point is, if you follow a really rigid, logical structure, you can do it very, very quickly. You're not trying to spend months building this stuff. I mean, we get the simplest possible thing we can in, and we test it, and we just spin around it really, really quickly. You don't need the whole system, you don't need the whole environment, but you do need your eyes open to what are the constraints about what the bits I have got, how do I think they'll behave, and just be aware of where you're going.
And the last thing is, don't get carried away. So I properly love doing this, so it kind of, people who I work with are surprised that I'm this sad, but because I didn't become a scientist and I ended up in IT, I love tweaking stuff and making it go faster and testing it to figure out where the bottlenecks are. And you can really lose sight of your targets. So with us, especially because we build software for other people, we need to make sure that we're not tuning the life out of something which nobody cares about when there's a thing that could potentially be slower, which isn't as exciting. So always going back to the key requirements, what is the thing you're trying to deliver is key. Because it's very exciting. You can get completely carried away.
So when you're done, again, the last kind of section is time to write it up, summarise what you've done and what you've found. Again, it's really important. It's really important for us because very often there'll be people following our footsteps, and you don't want to do a whole load of good work and someone goes, those guys from Capgemini didn't do anything. So actually it's really important to just be thorough. Someone will have to follow in your footsteps at some point. Try and be scientific, try and capture in a succinct way.
We bravely now decided we've proven it, whether you like it or not. So we'll move past quickly. So, any questions? And we're allowed to do this for hiring if anyone wants the job. So we've got 3 minutes left if anyone has any questions. Go, Daniel.
So really good presentation.
Thanks very much.
I see this a lot in my day job as well, and totally loving it. Any thoughts? You mentioned about doing experiments, sort of simple experiments up front. I see some people like Adrian Cockcroft doing simulations,
Yep.
Simian Viz, Monte Carlo simulations. What do you guys think of that? Good, bad?
So I'll let Kevin. So the question is, because we're supposed to repeat questions, do we see people like Adrian Cockcroft are doing, kind of taking this, pushing this to the next level, doing Monte Carlo simulations, Simian Viz, which I haven't even heard of. Every time I speak to you, I need to check stuff out. Things like that. And you're doing hardcore stuff, so you probably...
Yeah, so I think they're great, but I think if there's a spectrum of maturity, I think the vast majority of projects aren't anywhere near the top end. Sometimes you go into place and think, if we just did the basics, if we just made it repeatable, we'd be 1,000,000 times better off than we currently are. If we just wrote down what we've done, or we just wrote down what the configuration was, then... So I think my general thing is just do the basic stuff, but they're awesome things, and great if you can get to them, but I think you get the most benefit from just being thorough and do the basics.
Well, the way I corrupt people in my team into this kind of mindset is we've done things where, like kind of bug bashes and hackathons. So bug bash is kind of exciting, but they go, yeah, we're making the project manager happy. Stuff like that, and we have done things where we just go, right, it's the day when you get to beat stuff up, and like really try and break it. And not functionally, but break it non-functionally. People really enjoy that. It's good fun. So I haven't heard of that, but I'm going to try and, because we've like loads of the team. Sometimes now you'll see them and they'll be staying late because they're trying to break something that they think shouldn't break. So that's good.
Nice.
Any other questions? Yeah, go.
Kind of your process from going from like having none of this kind of testing all the way through to you've got it your CI going through every build and working like that. How do you get from the nothing to having the kind of thing that you're proposing?
So the question is, time's up. We'll keep going. The question is, how do we go from having zero of this to getting it all soup to nuts? Even going as far as Daniel talks about. So I can tell you how we do it. So I like I said, I test infect people. So if you make it fun, and it helps if you bounce around and talk about it like this, some people, not everyone, some people think it's the dullest thing in the world, but if you make them think that it's exciting, they'll do it. And you'll realize they'll start, things will appear in your build, so we let other people, there's no build guy, we own the build. So you'll start seeing Jenkins jobs, which are like perf testing stuff, and it might only be perf testing 2 or 3 things, but you look at it, you're like, oh, that seems to be testing the thing that I ought to have been worrying about a bit more, and now I don't need to because you can see stuff. Well, you'll see pull requests coming in which don't change the code. So that's for me anyway, making at least 2 or 3 people kind of excited about it. That's the big thing. Because again, like Kevin said, like and the bar is really low. Just like a few, JMeter tests with some kind of data, with something vaguely realistic.
But repeatable.
Because so the big thing we didn't mention, it needs to be checkable into Git. So we've got jobs which warm caches, we've got jobs which create data. So and then we chain them together using Jenkins. So there'll be like a Jenkins build pipeline which will check out the JMeter scripts. We'll then run run that Jenkins job to put the data in. Then another one which will run the Jenkins job to warm the caches, and then a third one which will run the test. And so that's good. And then we also know things like if we broke the API, because it's obviously coded against an API, we know, and things like that. So it's good.
We're up.
We're up.
We've got more
We're
questions.
being
Come
waved at.
and find us.
Come and speak to us. So we'll have no microphones on.
Very much.